In Lab 9, we're going to explore different types of chemical reactions. Starting off with Part A, we're taking a solution of lead-2 nitrate and reacting it with a solution of sodium carbonate. So using the pictures on this slide, you can write the descriptions of lead-2 nitrate, being the test tube on the top, and the description of sodium carbonate being the test tube on the bottom. Notice they're both clear, colorless liquids. Now, for a description of the reaction, you can see the reaction in the picture to the right, where we're taking the lead-2 nitrate and adding sodium carbonate to it. Notice you get a cloudy white substance. The next few questions ask you to write a balanced molecular equation, a balanced ionic equation, and a net ionic equation. So in case you haven't covered this in lecture yet, I wanted to explain a little bit on how to balance molecular equations. So here I have an example of a balanced molecular equation. So how do you go about balancing it? Well, in order to balance an equation, you add coefficients in front of each element or compound. And your goal is to get the atom count to be the same on both sides of the equation. What that means, in this case, the two elements I have present is aluminum and oxygen. So that means I want the same amount of aluminums on both sides of that arrow and the same amount of oxygens on both sides of that arrow. When I do my atom counts, you can see that this is a balanced equation. To get it balanced, I added coefficients in front of every element or compound. So this number 4 in front of aluminum is saying that there are 4 aluminum atoms. For the oxygen on the reactant side of the equation, I put a coefficient of 3. So the total number of atoms of oxygen on the reactant side, I have to take the coefficient and multiply it by the subscript, this number 2 in yellow here. So 3 times 2 will give me the total number of oxygens, which is 6. Now going to the product side, I want to make sure that I have 4 aluminums on the product side and 6 oxygens on the product side so that my atom count stays the same. So to do that, I add a coefficient of 2, this number in red. Now, to figure out the aluminums, I take that coefficient, multiply it by the subscript of aluminum, this yellow 2. 2 times 2 equals 4, so now I have 4 aluminums on both sides of the equation. Next, to get the number of oxygens, I take the coefficient that's in front of that aluminum oxide compound and multiply it by the subscript on oxygen, which is this yellow 3. 2 times 3 gives me 6, making the atom counts the same on both sides of the equation. The coefficients are the only things you can change to balance the reaction, the only numbers you can change. Never change the subscripts. So those numbers in yellow on this slide, those you can't change. If you change those numbers, you're changing the compounds themselves. So subscripts cannot be changed. So now I wanted to show you an example of the 3 types of equations that you're going to need to write for this lab. You want to start with the balanced chemical equation. So in the example I have shown, we have lead-2 nitrate, which is the same compound that you're reacting in Part A, but instead of reacting it with sodium carbonate, I have, in my example, it's sodium iodide. So when I react those two, what I get is a double replacement reaction, and I'll go over the types of reactions in a minute. What's happening is these two compounds are switching ions. So lead on the product side is going to be paired with iodine, and then sodium is going to now be paired with the nitrate ion, that polyatomic. So in order to balance the equation, we need to add coefficients in front to make sure we have the same number of atoms on both sides. When you're doing this with polyatomics, it's a good idea to keep the polyatomic together. So what I mean by that is this subscript of 2 that's outside of the parentheses of that NO3, that's saying there are 2 NO3s. So over on the product side, we add a coefficient of 2 so that we're saying there are still 2 NO3s. Now this coefficient of 2 is also saying there are 2 sodiums. So since there's 2 sodiums on the product side, we add a coefficient of 2 on the reactant side as well, so that we also have 2 sodiums. Notice for lead, there's just 1 on the reactant side, and there's also 1 on the product side. For iodine, the reactant side, the coefficient of 2 says there are 2 iodines on the reactant side, and then the subscript of 2 says there are 2 iodines on the product side. So all atoms are balanced. Now you'll also notice in parentheses these little symbols. So we have AQ and then AQ for both lead-2 nitrate and sodium iodide. So what AQ means is aqueous. So the reason that we put that after the compound is we're indicating what state that compound is in. So if you have a solution, which both lead-2 nitrate and the sodium carbonate that we reacted in part A are both solutions, you would write AQ. It means it's a solid dissolved in water. Now, over on the product side, notice we have S for lead-2 iodide, and we have AQ for sodium nitrate. So the reason we have S for lead-2 iodide is because that's a solid. And you can use your solubility tables to figure out if it should form a solid or not. Now we know a solid formed in reaction A that we saw because that white cloudy substance was actually a solid, a precipitate. So we know that one of the products in part A is going to be a solid, using your solubility tables to figure out which one. Then the other one by default will have an AQ by it because it's aqueous, it's still dissolved in the water. So how do you take this balanced chemical equation and write a complete ionic equation? Well, you separate all of the elements or polyatomic ions and you write their charges. So lead is going to have a 2+ charge. So how do we know it's a 2+ charge? Because of this subscript of 2. That is saying there that lead is a 2+. For NO3-, it's a -1 charge. How do I know that? Well, you can actually find that on your polyatomic tables. Now for the next compound, sodium iodide. Sodium has a +1 charge. It's in group 1 of the periodic table. It's a main group element. It's an alkali metal, and all alkali metals have a +1 charge. Iodine. Iodine, when it forms an ion, forms a -1 charge. It's a halogen. It's 1 away from being a noble gas, so it gains 1 electron to get a -1 charge. Notice that we also keep the coefficients in front of each ion. For instance, lead. There's only 1 lead atom, so there's a coefficient assumed of 1 in front of that. For the nitrate ions, that 2 outside of the parentheses. Notice now we put it as a coefficient saying there are 2 negative nitrate ions. Also 2 sodium cations and 2 iodine anions. Going to the product side of the equation. So on the product side, we leave the lead-2 iodide together. We're doing this because it's a solid, so it's not forming ions in solution. So the reason we're writing the other ones as ions is because they have dissolved in water and their ions are literally floating around in that water. So the only one we're going to separate and write the ions for is the one that has the aqueous symbol by it, which is sodium nitrate. Sodium we said was a +1, and the nitrate ions a -1. That coefficient of 2 tells us there's 2 sodiums and 2 nitrates. So this is the complete ionic equation. So how would you write the net ionic equation? Well, you cancel out any ions that are the same on both sides of that arrow. So for instance, we have two NO3s on the reactant side, so we can cross that out because we also have two NO3s on the product side. Same thing goes for sodium. Cross them out because it's the same on both sides, just like you see below. These are called spectator ions. Since they appear on both sides of the arrow, we can cancel them out to get our net ionic equation. So the net ionic equation is showing what ions are making up that solid, that precipitate. So write all the ions and compounds that are left after you cancel out. You'll be doing this for a few different reactions. So the question is asking you to label what type of chemical reaction happened in part A. So we have 4 different types, and you can find a list similar to this in your lab manual on page 51. So the first one is synthesis, also known as a combination reaction. So with a synthesis or combination reaction, you have 2 elements combining to form a new bond. Next, we have decomposition, in which you have a chemical compound decomposing into 2 or more separate compounds or elements. Now, the most common that we're going to see are single and double replacement in this lab. So for single replacement, you have a compound reacting with an element. So what's happening in this case is they're switching ions. So A here is partnered with B on the reactant side. So on the product side, A is going to partner with C. So now on the product side, we have A and C in a compound, and B no longer has a partner. So B is now by himself. Next, we have a double replacement reaction. So with double replacement, we have 2 compounds reacting together. So it's very similar to single replacement. It's just that now it's 2 compounds instead of a compound and an element. So 2 compounds, and now they're switching partners. So A and B are together on the reactant side, and then on the product side, A is now going to be with C. And then B and D will be together. So you're going to use that table on page 51 to identify what type of reaction is occurring in part A. Notice you have 2 compounds reacting together, and that will help you even predict the products, knowing the type of reaction that it is. So what you're seeing now is part B. Part B, you're taking elemental copper and reacting it with oxygen. We do this by introducing flame, so watch the video and record your observations. There is a question that says, in the previous lab, a crucible cover was used. Why was one not used in this experiment? Well, we're not doing these labs in order, so that's going to be a difficult question to answer. So you can go ahead and skip that one. If you choose to answer it, that's fine, but I won't count it incorrect if you have the incorrect answer there or if you leave it blank. So for that experiment, where you're taking copper and reacting it with oxygen, you need to write the balanced equation for the reaction. So when you write the balanced equation for the reaction, you're taking copper by itself, so it's not attached to anything, reacting with oxygen. And remember that oxygen in its elemental form is actually O2. So this type of reaction is called a redox reaction, or an oxidation-reduction reaction. And what's happening in a redox reaction is there's a transfer of electrons from one reactant to another. We often see redox reactions in single replacement reactions. So many single replacement reactions are redox reactions. That should help you answer the type of chemical reaction out of those 4 choices that we saw a few slides ago. Now, here's an example of a redox reaction so that you can see what's going on and try to answer the following questions. Once you write the balanced equation, you need to assign oxidation numbers to the reactants and products. So I wanted to show an example of how to do that. So here we have copper 2 sulfate reacting with elemental magnesium. And it's a single replacement reaction, so what's happening is magnesium is going to take the place of copper, so that now on the product side, magnesium is in a compound with sulfate, and now copper is in its elemental form by itself. So whenever you have an element by itself, so magnesium and copper in its elemental form, its oxidation state is going to be 0. When you have a compound, you now have ions, so you'll have charges. So for copper, in this case, when it's with sulfate, copper is going to have a +2 charge, as you can see in the half reactions below in that white box. We have copper with a 2+ charge. Magnesium, when it's in the compound on the product side, also has a +2 charge. We know this because it's an alkaline earth metal in group 2, and that's its most probable ion. So once you assign charges, you next need to identify which substance is oxidized and which substance is reduced. So to do that, you're going to follow the guidelines below. If you lose electrons, it is oxidized. If you gain electrons, it is reduced. So you're looking to see what happens to the elements involved in the equation. So notice we have copper. On the reactant side, it's a +2. Over on the product side, it's now 0 because it's by itself. So how does it get to be from a +2 to 0? Well, it's got to gain 2 electrons. Now I know that sounds counterintuitive, but think of it. You have a +2 charge and electrons are negatively charged. So what you're really doing is you're gaining 2 negatives. So a +2 plus a -2 equals 0. So copper is gaining electrons, so it is the substance that is reduced. Magnesium is going from a 0 to a +2 charge. So what we're going to see is that it's losing 2 negatively charged electrons to become that +2 charge. So magnesium then is oxidized. So here's a way to remember oxidation and reduction. So there's 2 mnemonic devices that you might have heard before. One is oil rig, and the other is Leo the lion goes grr. So these will help you remember that oxidation is losing electrons, reduction is gaining. Or if you prefer to use Leo the lion says grr, Leo would be loss of electrons is oxidation, gain of electrons is reduction, grr. So now let's look at oxidizing agents and reducing agents, because you also need to label which one was the oxidizing agent and which one was the reducing agent. So oxidizing agents cause oxidation. So what that means is whichever substance was reduced, so whichever substance gained electrons, it gained those electrons by oxidizing the other substance. So the substance that was reduced is the same as the oxidizing agent. The substance that was oxidized is the reducing agent. In this example here, we have copper oxide being reduced. So copper is going from a +2 to a 0. So since it was reduced, it is the oxidizing agent because it's causing oxidation. We have hydrogen. So hydrogen in this case, H2, it's in its elemental form, so its charge is 0. So it goes from a 0 to over here, a +1. So now it is losing electrons, so H2 is oxidized. Since it's the substance being oxidized, it is also the reducing agent. For type of chemical reaction, we just said redox reactions are most often single replacement reactions. Sometimes they can be synthesis as well, though, so pay attention to that. Most of the time, single replacement, but in this case, it might be a synthesis or combination. Reminder of those reactions, synthesis would be taking two compounds and taking two elements, and combining them to make one compound. Single replacement is taking a compound and an element, and you will get a new compound and a different element by itself. So pay attention. Do you have two products or just one? That will help you decide if it's a synthesis or a single replacement reaction. So in part C, we're taking elemental magnesium, solid magnesium, and reacting it with a compound, hydrochloric acid. So the first picture is magnesium ribbon. So it's the solid magnesium that we're putting in the flask. So please describe it in your lab manual. Next, we have HCl. Once we add the HCl, you're initially going to see bubbles. So that's not a precipitate that you're seeing. It's actually just little bubbles. So a gas is being released. When you write your balanced chemical equation for the reaction, note that one of your products is going to be a gas, so you'll have a G by it. Now, as the reaction progresses, you see bubbles still, and if you actually let it go the entire time, you would see that magnesium completely dissolve. So one of the products is a gas, the other product is going to be an aqueous solution. So it's going to be a completely dissolved solution. Now, if you were holding on to this flask during the experiment, you would actually feel it heat up because it is an exothermic reaction. Make sure you're writing that balanced chemical equation for the reaction, writing down the states. So make sure you're including your aqueous, gas, all of that. Magnesium's a solid, so you put an S by that. And then this is a redox reaction as well. So you need to identify which substance being oxidized and which substance is being reduced. Don't forget to assign oxidation numbers to the reactants and products. That's going to help you figure out which substance is oxidized and which is reduced, and then the oxidizing agent and the reducing agent. Type of chemical reaction, remember it's either going to be synthesis or single displacement for this one. So pay close attention to that. Now for part D, we have iron with copper 2 sulfate. So the pictures chosen, I chose just iron nails. So these are elemental iron, so Fe. We're reacting that with copper sulfate, CuSO4, copper 2 sulfate, And now notice it's a liquid, so that's why we have an AQ written by it, because this is in its aqueous form. So write the description of that solution as well. And right next to it, you'll see it says after reaction. So once we add these together, notice what happens to the color of solution, and then also notice what's happening to the iron nail. It changed colors, are you seeing any bubbles, anything that you see. You'll write the balanced equation for this reaction. So notice you're taking an element and reacting it with a compound. So you're probably going to see some partners switch over on the product side. Since it's a redox reaction, make sure that you are assigning oxidation numbers to the reactants and products, and then identifying the substance that's oxidized, the substance that's reduced, the oxidizing agent, reducing agent, and the type of chemical reaction. For type, don't put redox. I want you to put one of those 4 choices on page 51. So synthesis, decomp, single, or double replacement. All right, next, part E, heating of a hydrate. So what we have here is, I believe this is copper hydrate. I already forgot. Yes, copper sulfate pentahydrate. So notice it's blue crystal color. So this is when we started heating it. As the heating progresses, look what's happening to the color. Not only the color, but the crystals themselves. So we have nice pretty crystals in the first crucible, and then towards the end, they're white and it's more of a powder. So description before and description after. Next, it asks you to write the description upon adding water. So we took that white powder and added water, and that's what you see right here. So part of it's with added water, and the white part has no water added to it. You'll write the balanced chemical equation for this reaction, where we're removing water, and what type of reaction it is. Now for part F, last part, we're taking sodium hydroxide and reacting it with hydrochloric acid. So first we're testing the pH of both solutions. So describing the solutions themselves might be kind of hard to see. They're both supposed to be clear colorless liquids. Then we have sodium hydroxide, and there's a piece of pH paper being dipped into it. Very, very dark blue color. So using this pH scale below, you would find what color you think it is and then write the corresponding pH. For the HCl, we dipped a piece of litmus paper or pH paper in that as well, and you'll describe what color that is. Now I know it looks more pink, it's kind of more pink than red, but it should be in this range somewhere. So write what pH you think it is based off of that test strip. When you combine the solutions, you can see what's happening here. It's just going to be a clear colorless liquid again. We then dipped another piece of litmus paper to see the pH of the combined solutions. So take that color and compare it to the table and write what pH you think that is as well. Now the last part is to write the balanced molecular equation for this reaction, and also the ionic equation and the net ionic. So back what we did in part A. Don't forget to label the type of reaction.